We have a random load cell right here. We have a digital voltmeter right here, and we have our adjustable power supply right here. So yes, our random load cell. So if we look at it, we can see it's a 500-pound load cell. But that's all the information we get out off of it. It does have a Rice Lake part number. It's an RL50210A-500. We don't know what that means. We don't have a data sheet to go along with the load cell. We are going to use our brains, our meter, and the power supply to determine what exactly it is that this load cell is about. So we have wires. In order to really figure out how this load cell works, we need to figure out the color code. So we're going to turn on our meter. We're going to change to resistance. So usually 99 times out of 100, our black lead is negative excitation. So we're going to hook on a negative excitation. And again, another 99 times out of 100, our highest resistance between any two pairs would be our excitation. So we are going to clip onto red. We have 399.6 ohms. We'll try green. Green, we have 300. Red, we have 399.2. So between black and red, we have our highest resistance. So we can deem that, okay, black and red is our pair of excitation. So with that being said, what we can do now is we can apply an excitation voltage. So we're going to turn on our power supply. Let's get a nice, good, even number for excitation. We're going to apply 10 volts excitation to our load cell. So negative goes on negative excitation. Red positive goes on positive excitation. And there we go. So we have excitation voltage to our load cell. We determined what wire's excitation was because of their resistance. Again, the highest resistance we use to determine what excitation is. 99 out of 100 times, that is correct. Let us measure our input resistance as well. So we're going to put our leads across. So we have a 350 ohm input resistance. So we can now determine that this load cell is a 350 ohm load cell. Since we have everything set up nicely, we're going to test this load cell. So between excitation, we should have the highest resistance. Between signal should be the second highest resistance. So excitation was just about 400 ohms. Across signal or input is 350 ohms. So between any excitation and any signal, we should have the same resistance reading, plus or minus about 3 to 4 ohms. So we have minus excitation to plus signal. We have 300.8. Now we have 300.7. We're going to switch to our positive excitation and then go across both of our signals. Here we have 300.8, 300.9. So we're plus or minus 0.2 ohms, which is awesome. So let's go back. Let's rehook up our excitation. Negative excitation goes to our negative excitation. Positive power goes to positive excitation. So we have green and white left. So what we'll do, we will assume that green is positive signal and hook up our positive red lead to it, and we will assume That white is our negative lead. And so with turn this power supply back on. So we have 10 volts on our power supply, 9.98. Oops. Course adjust, 10 volts. And we will switch to DC millivolts. So right now, with nothing applied to the load cell, we should have 0 millivolts. There is no load on the load cell. So we should have 0 millivolts. We're at 0.1 millivolts. Could be the accuracy of my meter, or the load cell might be just small overloaded. But as you can see, when we push down on the load cell, we have a change in our DC millivolts. So we have DC volts going to excitation on red and black, and we have DC millivolts coming out on our green and white. So we have a 500-pound load cell. We know it's a 350 ohm load cell. We now know the color code of the load cell. So now let us try and determine what its load cell output is. So that would be its millivolt per volt output. So let's get a weight and we will figure this out. So we have a 25-pound weight. We are going to carefully place this on our load cell. The load cell is not mounted, so it's going to be a little tricky. So we have a change in millivolts of 1.5 millivolts. So we have a 500-pound load cell. If we divide 500 by 25 pounds, we get 20. So we multiply our change in millivoltage, our 1.5 by 20. That will give us our maximum output from the load cell, which we then divide that by our excitation, and we can get our load cell millivolt per volt output. So we take 1.5, we multiply that by 500 divided by 25. So 1.5 times 20 is 30. So we have 10 volts applied to our load cell. If we take 10 volts, take 30 divided by 10 volts, we get 3. So therefore our load cell is a 3 millivolt per volt load cell. If we can change and see this gradually, I'll try and place the weight on. So I'm going to change our DC power. Too far. To 5 volts. And that was half of our 10 volts excitation. So if you look on our meter, we have 0.8, 0.7. That would be half of our millivolt output that we had before. So proportionally decreasing our excitation voltage also decreases our millivoltage. So we've been able to take a random 500-pound load cell, determine its color code for wiring. Could also determine its millivolt per volt output, or the load cell output. And we can determine that the load cell is good and the load cell is not overloaded.